Hello, welcome to Fundamentals of Acoustics. Today is the 8th week of this 12-week course, and what we will do today and also in the subsequent weeks is a series of applications, or we will try to, that is what we will do is we will try to solve problems which have practical application in mind, and the intention here is that whatever you learn from this course you should be able to apply in your fieldwork or in some real situation, real types of situations. So, last week we had developed an expression for impedance, and we had also explained how using a Kunz tube you can measure the impedance of a material. So, that is one example of a real problem. So, if you have a particular type of material whose sound absorption properties are to be known, then you can use a Kunz tube and the method described in the last week to determine those properties of the material. This week we will focus on two important applications. The first application is that how do you reduce a sound. So, suppose there is a lot of sound in one particular area, and you want to make sure that adjacent to that area not a lot of sound is heard. So, how do you reduce the sound coming from a noisy area to an area where you want relatively less noise? So, that is one problem we will try to address, and the way we will try to address is by using a special method known as mass attenuation. So, that is one problem we will try to address. The other problem is that if you have a source which is emitting sound, for instance an engine or a blower, and it has a particular frequency which is dominant in nature, then how do you reduce this kind of a sound where one particular frequency is dominant? And this week what we will do is we will develop the groundwork for developing a muffler or a silencer for this kind of an application, and the next week, especially in the first half of the next week, we will actually explain how you can design a muffler to meet your application needs. So, the first problem we will try to solve is sound reduction, or probably instead of sound maybe the term noise will be more appropriate. Noise reduction by mass attenuation method. Okay. So, let us explain the problem. So, suppose you have a big room and there is some machinery here which is emitting a lot of noise. Then what you want is that, so this is a noisy area, and you want that here there should be low noise. So, we desire that this area should have less amount of noise. Then what do we do? So, a lot of times what people do is people put some partitions. So, people put, you can construct a wall or put a partition using a board or something, and then what you want to understand is that what will be the noise transmitted in this area. So, that is what the aim is. So, this is the problem we will try to address in the first part of this week, and when we do that, let us first set up the problem. So, we will discuss the method of mass attenuation. So the term attenuation means reduction. So mass attenuation. So the intent is that we, by using mass, we want to reduce the spread of noise from a noisy area to a area where we want less noise. So what do we do? So let's say this is a partition, and this partition is infinitely long. So it's a very wide partition, and so there is some source, and the source is emitting a noise, and such that there is an incident wave which goes and hits this wall. So the incident noise is P plus E minus j omega x over c times E j omega t, and when it hits this wall, some of the noise gets reflected. So I will say that the complex pressure due to reflected sound is E minus j, no P minus to the power P minus times E to the power of j omega x over c E j omega t. And then there is some noise which gets transmitted through the wall, and the level of that noise is the Pt, and it's moving in the positive direction, and that noise is, its complex pressure is Pt plus to the power of E minus j omega x over c times E j omega t. Okay. So what is it that we are interested in? We want to figure out how effective this wall is in terms of reducing the noise which is getting transmitted. So essentially what I am really trying to figure out is that what is the ratio of Pt to P plus, okay, Pt, and I am going to later drop this plus term for Pt because there is no reflected sound here. So I will just say Pt over P plus. So the assumption is that once the noise is transmitted, it is getting transmitted into an open field, and there is no reflecting wall. So on the transmitted side there are no reflections happening. So we want to find this ratio Pt over P plus. If Pt over P plus is less, then the wall is doing its job very well. If Pt over P plus is high, and the maximum it can be is 1. So if it is 1, then all the sound which the wall is receiving, it's transmitting it faithfully to the other side. So that kind of a wall is not a good noise reducer. So that's our problem statement. So our goal is to find out this ratio Pt over P plus. So we will now simplify this picture, and if I look at this picture from the end, then this is how it looks like. Okay. So this represents the wall, and this wall is infinitely long and infinitely deep, okay, but its thickness is limited. So its thickness is d, and there is a sound source which is generating noise, and because of that noise there is an incident pressure field which is, and the complex incident pressure field is E P plus times exponent minus j omega x over c times E j omega t. There is a reflected thing P minus exponent j omega x over c E j omega t, and then we have a transmitted sound pressure, so which is Pt E minus j omega x over c E j omega t. And let us say that x is equal to 0 at the wall, and this is the direction of positive x. So, I have defined my coordinate system. Then we make some assumptions. So, what are the assumptions? The first assumption is that d, which is the thickness of the wall, is very small compared to lambda. So, if I am striking this wall with a particular frequency, the thickness of the wall is extremely small compared to the wavelength of the wall. What does that mean? That when sound travels through the wall, it will take some time for sound to travel from one side to the other side, and as it travels over that period of time, the change in phase in the transmitted wave will be extremely small. If d is extremely small compared to lambda, if d was equal to lambda, then the phase difference would be 2 pi radians. If d was lambda over 2, then phase difference would be pi radians. If d was lambda over 4, then it would be pi over 2. But if it is extremely small, then the transmitted wave's phase will be more or less same at x is equal to 0 relative to the incident wave phase. Okay. So, what that means is then as we are doing the mathematics, we do not have to account for the phase difference which is introduced due to the thickness of the wall. So, if d is very small compared to lambda, then we do not have to worry about change in phase over distance d in wall. Second thing we assume is that m is equal to mass per unit area of wall. Okay, it's mass per unit area. And the third thing we assume is, so let us call this side A, and on the transmitted side we call side B. So, Z on side A is equal to Z on side B, okay, is equal to Z naught. So, ZA and ZB are characteristic impedance. So, media on side A is same as media on side B, which means characteristic impedance on side A, side B is same as Z naught, and that is air. So, it is equal to rho naught C, where rho naught and C naught are correspond to density and speed of sound in air at STP conditions. So, with these assumptions, what we are interested in finding is this ratio PT over P plus. So, this is what we are interested in finding. Okay. So, what do we do? How do we start solving this problem? So, the first thing is that we look at side A and look at side B, and we develop the transmission line equations for both side A and side B. So, for side A, P, and I will call it PA xt, and velocity on side A is UA, so this is complex pressure on side A and side B. This is equal to P plus, P minus, P plus over Z naught minus P minus over Z naught E minus j omega x over c E j omega x over c E j omega t. Similarly, for transmitted side, PB is same as okay. So, PB xt and UB. So, B corresponds to the transmitted side, the other side of the wall, that is equal to. So, on the transmitted side, what is the incident wave? PT, and what is reflected wave? There is none. So, its amplitude is 0, complex amplitude. So, 0 PT over Z naught, 0 E minus j omega x over c, E j omega x over c, E j omega t. So, let us look at these equations. So, the first set of equations is for side A, the second set of equations is for the transmitted side. These are total of 4 equations, and the number of unknowns in these equations is, so we do not know of course PA, we do not know UA, we do not know P plus, we do not know P minus, then we do not know PB, we do not know UB, we do not know PT. So, total of 7 unknowns, and equations is 4 equations. Okay. So, if we have to find all these unknowns, then I have to know 3 extra conditions. If I have to just find the ratio of PT and P plus, then I have to know 2 extra conditions. So, to find PT over P plus, we need 2 extra conditions. So, 4 equations and 2 extra conditions will give us sufficient information to find the ratio of PT and P plus. Okay. So, that is what we plan to do. So, what are those extra conditions? So, the first extra condition is that at x is equal to 0, at x is equal to 0. So, let us look at this point. At x is equal to 0, the air on the wall, the pressure on the wall, whatever is the velocity of this wall will be same as the velocity of air on the right side, and it will be same as the velocity of air on the left of the wall. Okay. And it is not 0 because the wall is free to move, because it is free to move. Okay. So, when I put a partition between 2 rooms, if some pressure is being applied on the thing, unless the wall is rigid, but if wall is free to move, then it can move back and forth, even though that distance, displacement and velocity may be small, but it is free to move. So, whatever is the value of velocity on left side of the wall is same as velocity on the right side of the wall. So, that is our first boundary condition. So, first boundary condition is velocity of air on side A at x is equal to 0 equals velocity of air on side B at x is equal to 0. Okay. This is the first boundary condition. So, what do I do in this case? This is equation A, this is equation, okay, so I do not want to use A and B again, it will create confusion. So, let us say this is equation 1, this is equation 2. I can calculate the expression for velocity from 1 and 2, and at x is equal to 0, these two numbers are same. So, I can equate them. So, that is what we will do. So, U A at 0 t is equal to P plus by Z naught, and if I put x is equal to 0 in exponential terms, E j omega x and E minus j omega x, everything will be 1. So, what I will get is P plus minus P minus divided by Z naught E j omega t, and that equals velocity on side B at x is equal to 0, which is equal to Pt over Z naught E j omega t. Okay. So, this is complex velocity. So, if velocity is same, then complex velocity has to be same. So, from this what I get is that Pt equals P plus minus P minus. So, this is one relation I get, this very important relation. So, this is equation 3. So, if I put 3 in 2, putting 3 in 2, we get, so what do we get? We get Pb xt equals P plus minus P minus E minus j omega x over c E j omega t, and ub is equal to P plus minus P minus divided by Z naught E minus j omega x over c E j omega t. So, this is a fourth set of equations. So, at this stage, so what we have done till so far is we have developed our equations for complex pressure and complex velocity, and to those we have applied the first condition at the boundary, that velocity on right side is same as velocity on left side, equated these two, and in that way I could develop a relation between Pt, P plus and P minus, and you have, using that I have modified or reframed the expressions for pressure and velocity on side B. So, with that we close our discussion for today, and what we will do tomorrow is continue this discussion and apply the other condition, one more condition, and then use that extra condition to solve for the ratio Pt divided by P plus. So, that is all for today, and we will meet once again tomorrow. Thank you.